try this out. So today we're going to do some integrals with respect to what's called Euler's equation, which is e to the ix is equal to I sine x plus cosine x. All right, so looking at this equation, you may ask yourself, wow, how can I use this to integrate my trigonometric functions, right? Well, the first thing you must, we'll just take this as a tautology, by the way. You can prove it with infinite series, a bunch of different ways, yada, yada, yada. I think my most favorite way to actually prove this is via differential equations, and maybe I'll make a video on that because it's very fun. But we'll just take it as a tautology for now. Now, the first thing we must do is, first and foremost, we know that the integral of sine of x dx is equal to negative cosine of x plus c. Now, I'm just going to throw this in here because, there'll be times where I do forget the plus c. The reason why we add integration constants is because if I were to differentiate this function, which I will go ahead and do, since this is what's called a linear operator, I'm able to take my operator, which is the derivative, and apply it to each of these individually, right? So I take the derivative with respect to x to negative cosine of x plus the derivative of with respect to x of a constant, right? But as we know, the derivative of a constant goes to 0, right? So for those of you out there that don't know really why we add that plus c, it's just for that, right? A constant doesn't actually change anything once I take the derivative. So we just added there because it doesn't really change the actual integral. Going forth with this, we know that the derivative of cosine of x is negative sine of x with a negative on the outside. We know this gives us back sine of x. And wow, we took the right integral. Anyways, that's just a side tangent. Let's move forward. So we are going to see how can we use this Euler's equation to integrate something that's very simple, right? And this may or may not help you in your trigonometric classes, but we'll go on. So the first thing we must ask yourself is, what does sine of x equal in this formalism, right? And I will just give it to you, and then I'll show you that it does indeed equal that, right? You can say that sine of x is equal to e to the ix minus e to the negative ix all over 2I, right? And let's prove this, right? We have the time to do so. We should prove it, right? So I gave that to you, and now let's prove it. So we know e to the ix is I sine of x plus cosine of x. And then we know e to the negative ix can be thought of this way, right? We're going to use our exponential algebra, right? So I'm going to rewrite e to the negative ix over here, right? And what we're going to do is we're going to rearrange this to say this is e to the I times negative x. And the reason for that is because we want to make sure our argument on the inside of our trigonometric functions takes in that negative, right? So if it takes in our negative, we're going to get I sine of negative x plus cosine of negative x. Now, we must think back to our algebraic rules of even and odd functions. If you've taken calculus 2, you will know that actually, if you've even trigonometry, it really pops up mainly in calculus 2 when you start doing Taylor series, where you see that sine is what's called an odd function, right? And since it's odd, it has the property that f of negative x is equal to negative f of x. So this becomes negative I sine of x. An even function such as cosine, we say f of negative x is equal to simply f of x because it's even, right? And this property comes from, for example, x squared. If you have an even power, oh, negatives don't matter, right? Square it, it gets positive back out. So this is simply just plus cosine of x, right? So all of that simply So we can write it above, and you'll notice something amazing happen, right? Because it's minus e to the negative ix, this becomes minus negative I sine x plus cosine of x. But if we distribute this negative, this becomes positive, and this becomes negative. And then don't forget all over 2i. I should just take that off right there. Great. So now we say, whoa, we have a negative cosine here, a positive cosine here, and we have two copies of this sine of x. So what we get is 2i sine x over 2i. Well, we can just simply cancel that out, and we get this is equal to sine of x. What a beautiful formula, right? So now we've established that this is true, right? We've established that sine of x is equal to e to the ix minus e to the negative ix all over 2i. And you might think to yourself, okay, Ramin, that's way more complicated than just simply sine of x, right? And the power of this notation comes from this, right? Let's say I ask the question now, what is sine of 2x, right? And we know, personally, if you should have some of these memorized, and this is where the power comes though. What if you didn't want to have this memorized to be 2 sine x cosine x? This is the beauty of it. Because I have this notation, sometimes, and actually most of the time, exponential algebra is easier than trigonometric algebra. So you can write this as 2 sine x cosine x, or simply do what we did before. I'm going to throw my argument in wherever I see this x. So this becomes e to the I 2x minus e to the negative I of 2x all over 2i. And with these simpler ones, it really doesn't improve your life that much, right? Because, for example, if I were to integrate this one, I could just do a u sub, right? So this is just an intro video to get us started, to see the power of it. Okay, and then now finally, we can do the same thing for cosine of x, right? Well, we know cosine of x should also have a similar formula. And this one, I'll let you prove on your own, right? I wanted to do this one because sometimes this 2i can be tricky, but you should prove this one on your own. It's simply e to the ix plus e to the negative ix all over 2. And you'll notice some similarities, right? This one has a 2i because the sine picks up the imaginary part of Euler's formula. And the reason for this, and I'll just dive into a little quick tangent, right? If we go to the complex plane, we actually make this our imaginary part, and this is our real part. Now, think back to how you first defined your trigonometric function on the real plane, right? If we go back there, and we use a different color for this. If we go back there, you would have realized that, where should I write this? I'll do this up here, right? If you go back here, you realize a point in the xy plane can be described, and we'll say this is a unit circle. So our radius is of 1, and this is our y-axis, and this is our x-axis, and we have some theta here, right? And we said, if I were to ask myself, what is sine of theta? You would get, your SOHCAHTOA, so it would be the opposite, and we'll call this xy over here, over the hypotenuse, which is just 1. Or in other words, sine of theta is simply the y contribution of your right triangle. So that's why in the imaginary plane as well, it picks up this imaginary constant, because we make the vertical axis in the complex plane to be imaginary. So it picks up the I, and that's how I think about it, right? So that's how I can always remember what sine of x is and what cosine of x is. It has to be the real, because in the complex plane, I don't know, I erased it, our x is real, so cosine is real, our sine is y, which is imaginary, so it must be imaginary as well. Anyways, these are the basic formulas you will use throughout the following video. So this is just an intro video to get us started with this fun concept. In the next video, you'll actually go through and integrate different variations of sine and cosine, and then we'll eventually go to cotangent, tangent, and all those fun stuff. See you next time.